Hello. Um, I hope you had a wonderful week. So let's start. Let's go to our module. So in we're still in module 2. Today is lecture 5. If you click on lecture 5, you'll see I haven't actually uploaded the videos. So you'll see all the videos here. And today in this lecture, we're gonna do two experiments. So first one is short circuit test, which is experiment number 3, and then a transformer regulations. So that is experiment number 4. So let's start with short circuit test first. So it is a continuation. So there are some tests that in practical field also engineers do. So one of them is open circuit test, and another one is short circuit test. So this is super important. So I have last week we have covered open circuit test, and this week we are gonna talk about short circuit test. So it's a pretty straightforward test. So in open circuit test, what we did is we supply voltage to one of the sides. It could be low voltage side or high voltage side, and we kept the other side open, and we measured the input side's voltage current in order to calculate core loss components. So those are whichever we calculate, like say for example, these R and X, these are core components. So today we're gonna do the opposite. We're gonna short one of the sides, normally the low voltage side, so that the amount of current passing through the short circuit is very low. So we normally supply to the high voltage side and measure the supply voltage, supply current, and also the power that goes into the transformer. And we short the other side, which is the low voltage side, and we calculate according to those measured values. Like say for example, we will measure power, we'll measure input current and voltage. So, and also since we normally use a power analyzer, so we can also measure cos theta, which is the power factor directly. So we don't need to calculate. So after getting that, the equivalent circuit of a transformer for short circuit test will look like this. So there will be an equivalent resistance and there will be an equivalent inductance. So this reactance is inductive definitely, and because we are talking about coils winding, so the nature will be like this, and mm, this is the equivalent for both primary and secondary. So we do it um, from the primary or from the secondary. If we measure, like say for example, we connect the low voltage side to the power supply and we short high voltage side. In that case also the value of R equivalent and X equivalent will be same. So these are the equation we are gonna use. There are two ways to calculate, just like the open circuit test. So this will be considered as way 1 and this will be considered as way 2. So I will show you, I will explain both of the equations, sets of equations. So we when we um, supply a fraction of the voltage, so it's very crucial that in this experiment we need to actually supply a fraction of the voltage, because otherwise if we supply uh, rated voltage, in that case the short circuit current will be huge. We don't want that. We don't want our setup to burn. So we actually measure the current, the short circuit. The setup has to be like this, that this the short circuit current, this ISC, will become equal to rated current. So the rated current should be the standard. So that is our target point. We will supply a small amount of voltage just to see what the current is. Then we'll gradually increase the amount of voltage so that the short circuit we get short circuit voltage or short circuit current or rated current. So normally the amount of voltage is 10% and no more than 10% of the rated voltage. If we supply 10% of the rated voltage, we actually get um, what is it called? The rated current. So these are the equations. If we look at this equation, we see power of short circuit that will be measured in our test case, and I short circuit definitely will measure that one. So with this, from this equation, we can definitely easily we can get R equivalent. So it can be calculated just like that. And for X equivalent, so we need to actually calculate this one first. We'll use this one, but we need to calculate this one first, just like the open circuit test. So this is nothing but the apparent power square minus real power square or active power square, and then if we root that, we'll get Q, which is a reactive power component. So after getting this, if we put the value here, we can get X equivalent. So that is, and we can, the combination of this will give us impedance. So this is one way to calculate R equivalent and X equivalent. There is another way we can actually calculate using supply voltage, supply short circuit voltage, and supply, not supply, the I short circuit, the current that circulating here. So we can actually get Z equivalent. And we already know this R equivalent, and now we know Z equivalent. From these two equations or these two values, we can easily calculate X equivalent. So there are two ways to calculate. So I want you to actually use both of them. So what are the procedure? If we go to lecture and if we click on experiment 3, what we're gonna do is there are procedures written here. I'm not gonna read out loud those. The first thing is you need to connect everything like this figure. Connect the power analyzer here, supply voltage slowly, step by step. We'll supply voltage to the circuit so that the current goes to not go beyond 1 ampere. So the current has to be within that range. So we'll supply the voltage until the current reaches 1 ampere, and then we'll stop and collect those information. Now I'd like you to sorry, just a second. So I'd like you to draw a table which will look like this one. Okay. Oh, so these are the formulas of way 1, and these are the formulas for way 2. So I'd like you to use both of them and draw a table which will look like this. So there will be measured values. So VSC, ISC, PSC, and theta, cos theta. So I'd like you to calculate QSC Z equivalent 1. Why I put Z equivalent 1? Because it will give you the values with using way 1 equations. So there, I know that both of the way will, like these way 1 equations and way 2 equations, they will give identical result, but it's better to learn both ways, right? So that's why I'm giving you this. And this is the equivalent circuit. So now I will play the video of the experiment that I have conducted for you guys. Let's see that. Hello. So this is the experimental setup for the first experiment, which is the short circuit test. We have done open circuit test last week. This week we're gonna do short circuit test, and this is the setup for this one. So we have power supply. So this is coming to the input of the power analyzer, and the output of the power analyzer goes to the primary side. So this side has to be the high voltage side, so we'll short the low voltage side. So we have use these banana cables to short it, and that's the circuit. So we are gonna test it. So for so in theory that I've explained already, I've mentioned that the supply voltage has to be no more than 10%, 10 to 15% of the rated voltage. So in that case, it cannot be go beyond what is it called, 25 to 26 volts. So we are good till that point. And there is another thing. So the ampere rating of the primary side has should be within 1 amp. So not within 1 amp, like 1 amp is good enough. So we're gonna connect it. So let me connect this one. So that one is also connected. Let me switch this power analyzer on. So everything is live. So I'm gonna dial up the voltage. So it's 16 voltage right now, and the ampere value is 0.6. So I can increase it a little bit so that the ampere value goes to 1 amp. Okay, that's about it. So with 25 volts I get 0.99 amp. And what about the power? So the active power for the primary side is 23.8, and the power factor is 0.96. So that's about it. So that's the measurement and experimental setup of short circuit test. Thank you. So that's the video for the short circuit test. Let's go back to the lecture. So yeah, so we have measured power, current, input current, and voltage, and cos theta, that is the power factor. So I want you to actually calculate all of them. So in your report, I would request you to, you don't need to put this discussion, that's not necessary, but I want you to actually give those formulas, way 1 and way 2. I don't need this part. I would recommend you to write down this procedure and answer these questions. Let's read out the question 1, discussion of full load copper loss and the equivalent circuit. So so in this experiment, what this R equivalent and is Z equivalent or X equivalent, this will determine the copper losses of a transformer. So since we have covered the short circuit one, so that means it is we actually covered full load copper test. So so we can calculate that one by using those formulas I've given. The schematic of the equivalent circuit. So I'd like you to actually draw the schematic of the equivalent circuit that I showed you. So I want you to draw that one. I'm definitely talking about this one, this circuit. And a table of all meter readings. So the table will look like this one. So HVS means high voltage side, and calculation for REZE and XE. And I want you to calculate all of this and refer to the secondary. So I want you to calculate REZE and XE for the secondary, because we are supplying everything from the primary. So we are looking at the circuit from the primary side, but I want you to do it for the secondary. So there are equations. If you cannot answer this one, I guess it is okay, but in theory, I hope that you know this how to do it. So I'm requesting you to do it. But if you cannot do it, it's also okay. You can ask me how to do that. I will actually explain that in another lecture if it is necessary. But I hope in your theory class you've covered this. So your teacher covered this already. So let's see. So that's about it for lecture, not lecture, like experiment 3. So we're gonna do experiment 4 now. So experiment 4, I told you it's about voltage regulation. So let's open that one. So this is experiment 4, and this is about voltage regulation. So what is voltage regulation? So voltage regulation is uh, a way to say that transformer is how a transformer is behaving. So it discloses the merit for a transformer of a transformer. So so normally, say for example, if I'm a sprinter without having any load, if I wear a shorts and a tank top, I can run very fast. But if you give me 10 kilograms of weight to carry, then I will not be able to actually run as fast as in case of when I wear a shorts and a tank top. So with load, we'll test our transformer with load and without load. We'll see, and with load, there are some changes in transformer's characteristics. So we'll test it with load and without load and compare the output voltage. So that means V2. So 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 this is the equation. So let me open another slide. Let's see. Okay. So I actually took a lecture. I gave a lecture in the morning, so I took a snapshot of that one. So I thought to myself, okay, let's take a picture and it will be helpful for you guys. So this is our experimental setup for uh, the voltage regulation. So we're gonna supply uh, with V1 voltage from the power supply. That's our power analyzer, and this is E1, which is the induced EMF on the primary side. And after transferring power from the primary to secondary, we get another induced EMF, which is E2. And finally, if we have a load, in that case, we'll get uh, uh, secondary current and secondary voltage. So for that to be calculated, we use power analyzer here again. So after that, we'll have another voltage, which is the secondary terminal voltage. So in practical cases, in practical case, V1 will be larger than E1 because there will be some losses in the winding and those copper loss as I have talked about, and there will be some losses here as well on the secondary. That's why E2 will always be larger than V2. But if it is an open circuit, in that case, E2 will be V2. Okay, so uh, we will test this voltage regulation experiment in 3 sections. So there will be, first we'll test the whole thing with R load and then RL load, and we will disconnect everything and we'll have open circuit. We'll test it with that setup. So with R load, we will switch this off on. So S1 will be on. In that case, the current will circulate only to R load. And then for RL load case, we'll switch this on as well. So R and L will be parallel. And if you look closely, this R is variable and this L is also variable. So uh, in case one, we will use only R load, and in case two, we'll use only we'll use R and L load. So in that case, it will be RL load. And in case three, we'll open everything here. So this will be an open circuit, and we'll measure the output voltage, which will be, in theory, V2 will be equal to E2. So, and the formula, the voltage regulation formula is like this: VNL, which is a no load voltage, minus V full load voltage. So in case of a no load test, if we see, if it is open, and then in that case it is called no load, so there is no load, right? So this will be exactly like E2. E2 will be exactly like V2. Okay, so normally that's a larger quantity. And full load means if we have maximum amount of load here, in that case, uh, the voltage value will not be equal to so V2 will not be equal to E2. It will be slightly smaller. And we'd like to see for R load what is the voltage regulation using this formula. And secondly, also for RL load, we'll use this formula to calculate voltage regulation for RL load. So for open circuit, we can definitely directly calculate V2, and that will be E2, definitely. But I want you to calculate also using this formula. Like for instance, for R load, E2 will be E2 or no load at no load will be V2 plus I2 R equivalent square plus I2 X equivalent square. So you may ask, where is R equivalent? Where can we get R equivalent and X equivalent? So we just covered short circuit test, and we have actually uh, we discussed that how can we calculate R equivalent and X equivalent. That is the R equivalent and X equivalent of this transformer that we are gonna test for to measure our voltage regulation. So if we use those information and put it here in this circuit, we can definitely calculate E2 for R load. And we're gonna do the same for RL load, and this is the equation. We're gonna, this cos theta, definitely we will have to remember we are doing all this for the secondary side. So this will be, this cos theta will be definitely this cos theta. So cos theta and V2 I2 times R equivalent that we get from, we normally get it from short circuit test. We'll square them, and we'll use this. We from this we can definitely calculate sine theta, and V2 will multiply them and add them with this amount, and we'll square both of them, and we'll after that we'll root them, we'll get this one. So interesting thing is, so E2 no load for RL load and for R load are the same. So we'll use this formula to calculate. So we'll compare whether this E2 and this E2 and this V2, whether they are same or not. That is one of the tasks. So we'll see, we'll observe our for R load, what is the voltage regulation? For RL load, what is the voltage regulation? We'll compare the results. We'll see what are the errors. We'll try to find out what are the errors. because theoretically uh, the the result might be different, but in practically after calculating everything from the measured value, we'll see the result might be different. So we'll have to do an analysis of those errors, as well as the another crucial thing is we'll have to compare the results E2 of this, E2 of that, and open circuit V2. We'll have to compare. They're supposed to be equal. If they are not, then we have some problem. There are some errors. You will have to identify why is that. Now I will open the video of this experiment. Let me open that. Okay, so this is the setup for the second experiment, which is calculating the voltage regulation. So the theory part I have already covered. So all I need from you is to actually get those data, get the data that I'm about to show you. So I will let me introduce the circuit first. So this is the supply coming to this power analyzer, and this is going to the primary side of this transformer, and the secondary side is going to the second power analyzer, and the output of this power analyzer goes to the load. So we are gonna use two types of load. So initially for case 1 we're going to use R load only, then we'll use another parallel load to this one, which will be L load. So first I'd like you to actually take reading of the values for R load, and then we'll connect the what is it called, L load, and then with RL load we'll measure everything again, and then in third case we'll do open circuit test. So and we'll make a table. I already showed you that table, and you need to put those values in that table, and after that we'll do some calculation that I have already explained. That's about it. Okay, let's start. So first with R load, so let's switch it on. Always make sure this the supply voltage is at 0 point. So in this case we're gonna supply 120 voltage for 3 cases. So with R load we're gonna supply 120 volts. Let's go for it. So 120 volts. Okay, that's 120 volt. So in the supply side, that means the primary side, this is the power 11.3, this is the power factor 0.97, supply voltage is 120.1, and this one is the supply current, which is 0.098. And what about the secondary side? So on the secondary side, if you look at it, so the power is 10.7, and there are some losses. Power factor on the secondary side is 1 because we are using R load, and then the voltage on the secondary side is 59.2, and the ampere rating is 0.173 amps. Okay, so we are in that case the maximum amount of current on with this load, I have switched every load here. So with this load the maximum amount of current is 0.173. so that's all I need. So now what I'm gonna do is I will switch the circuit off, and I will connect this L load with this R in parallel connection, and we'll measure everything from the start. Okay, so the connection is done. So this is parallelly connected with this new L load. So, and if you look closely, this is lagging, so that means we are choosing L load here. So if we go beyond this 0 point, 0 point means the value of L and C are equal. So if you go beyond this point, if you dial it up to the lead section, in that case that means the value of capacitance of this section is larger, but we want to measure everything with L load and R load in parallel. So that's about it. So we will connect this circuit. So everything is connected right now, and I will turn this on, and the input side is 0 because I haven't actually dialed it up. So I will check everything, and the supply voltage has to be 120 as I told you guys. So 120, let's go. So it is crucial to make it 120. Okay, so okay, it has to be a little bit less. Okay, let me try to get exactly that amount. Okay, that's about it. So the supply voltage is 120 and the power is 12.4, but we'll have to adjust before actually taking the reading, because in this system now we have introduced lagging load. So the amount of current is 0.2, but in order to actually measure calculate the voltage regulation, the output voltage, we will actually compare the output voltage. So that's why the current has to be equal to the current that we have actually measured for R. So now the current is 0.2, which is a bit larger, so we'll have to adjust the loads in order to get the current to be 0.17. So we will reduce the amount of inductance and to be when the power factor is 0.8. so let's see the power factor went down, so we'll have to adjust it. Like for instance, we'll adjust the power factor to be exactly 0.8 and the current should be at around 0.17. so it's quite close to the target measurement, but we need to adjust a little bit more. So this is the power factor. If I change the value of inductance, if I increase the value, so the power factor goes down. So I'm increasing the value, so the power factor is now 0.8. Let me look at the current. So it is 0.18, which is a little bit higher. So we'll have to reduce the amount of resistance. So initially we actually triggered all of them. Now we are actually switching off couple of them just to make them like when we actually measured the values of resistive load, we have to, the current has to be identical and the power factor has to be 0.8. so the power factor went down a little because we reduced the amount of resistance. So now let's pull it up. So the power factor is now 0.8 and the current is now 0.167, which is close to, let me see, okay, that's about it. So the current is 0.17 and the 0.171 and power factor is 0.858. That's good. So now we are I'm happy with the circuit arrangement. Now let's take reading from the left hand side. That means the what is it called, primary side. So primary side's power is 0.92, power factor is 0.767. here the voltage is 119.8. let me bring it up a little. Yeah, and the current of the primary side is 0.1. power of the secondary side is 8.8. There are some losses. Power factor is 0.858. Supply voltage is 59.6. Sorry, not supply voltage, secondary voltage. V2 is 59.5 and the current is 0.172. Now we're gonna remove everything from the secondary side, so we will open we'll make it open, so we will measure the output voltage. So let me dial everything down, switch it off, remove the connection of the secondary. Because we need to actually measure the value of the output, so we'll connect it to the power analyzer, but we'll disconnect everything from the output side, so we'll get rid of them. So there is no load, that means it is an open circuit. So now it is open circuit. So now let's switch it on, dial it up. The voltage is 120. Yep. So in that case, all we need is the input power 0.6, the power factor 0.415, the power supply supply power is 120.4, current is 0.012. And if you look at the secondary side, then you will see that the power is 0.4. There's power factor is 0 because it is open circuit. So, and the voltage here is 52.4. Okay, that's about it. Okay, thank you. Actually, I made a mistake, so I did the same thing, like the open circuit reading. I made a mistake in connection, so I did it second time. So that is the video. Okay, I've made a mistake here. So I actually connected the secondaries connection while doing the open circuit test. The secondaries connection, it was here, it was connected, that this banana cable was connected here, so I didn't get all the voltage, so that's why it was 52. I was a bit shocked, but now I'm gonna redo everything. So the supply voltage is about 120. So okay, with that the input is 0.6 watt, 0.415 is the power factor, 120.9, oh sorry, 120.3 is the input voltage, and this is the input current. And if you look at the voltage, now we see the secondary voltage is 60.4. So this is supposed to be the correct voltage. So what I did is, like, I actually, let me disconnect, and if I connect it here, so I'm actually losing some N2, so that's why the voltage was 52. So if I make it the connection like this, so this is the correct connection, so with the correct connection the voltage is 60.4. so that's about it. Thank you so much. Okay, so we'll use this measured value, we'll calculate them. I already told you about the equation, so we'll have to use them to. Okay, so we're gonna use those information and use them to make a table like this one, and we'll calculate voltage regulation, and these E2 and E2 will compare the result. We'll do some error analysis. So let's go back to the lecture. So For the report, I don't want you to actually write the discussion part. You can write purpose, experiment number, name, purpose of this experiment, procedure. Then in the report, you need to actually answer these questions, and there will be some additional questions I will give you in the assignment. You'll have to answer them all. So if you have any question regarding this one and these two experiments, so and you can ask me anytime. And another thing is, you'll have to, there will be two assignments for this week. So on experiment 3 and experiment 4. So you'll have to write everything and be specific on the answers. Like you don't need to actually explain everything. Like for instance, if I ask you to write error analysis, you'll have to be very precise with that one. You don't have to write an essay. You can write with like within one paragraph, you can explain everything. So that's about it. If you have any question, you can ask me anytime. Um, okay, have a nice weekend. Thank you so much.